Good morning, everyone. My name is Michael, and I am a student from Canada College, and this is.
Untitled Tariq, and a former student of Canada College, and right now I'm attending San Francisco State University.
And today we are going to talk about our research project done last year during an internship and in San Francisco State University called Logic Design Using Spin Transfer Torque Technology for Hardware Security Applications. Um, this group consisted of 2 members, but lamentably 2 of them were not able to come here and participate. So we'll be in charge of delivering the whole information of this presentation. So this is the outline of our presentation. The 4 most important parts that we're going to cover today are background, purpose of research, results, and conclusion. So this is the first part of the background. The idea behind this research project is to protect the intellectual property of integrated circuits, also referred as microchips or chips, from hackers or competitors who may reverse engineer them. Intellectual property security is becoming an increasing challenge for semiconductor industries, which are industries who design and sell chips while outsourcing the fabrication into external manufacturers. They can benefit from this security, and they will be able to protect the intellectual property. Now, these pictures can explain in simple terms the idea of this project. In old days, the concept about security was about keeping the physical entity safe and secure. But these days, it's about keeping the concepts involved, the design, the knowledge, and the functioning safe. Now, this is a picture of the process of fabrication of an integrated circuit. In this picture, I want to give you an idea of what the final state of the design of an integrated circuit is and where the threat is to industries who made them. If you can see here, the first row corresponds to the design process, whereas the second row corresponds to the fabrication process. Both processes are done in different entities. The first one, as I said, are done in semiconductor industries. The final state of the design is the layout geometry, which looks like this picture. Now, the threat occurs when this layout geometry is sent to foundries or external manufacturers. There is a high probability that the layout geometry can be exposed or stolen by competitors. Now, this is the second part of the background, and also the technology that will allow a safer mass production of integrated circuits. This technology is spin transfer torque random access memory, or also called STT-RAM. Now, as you may know, RAM stands for random access memory. It is a memory that stores information in the form of electric charge, and usually looks like the following picture. Random access memory can be volatile or non-volatile. Now, a recent technology based on non-volatile random access memory is STT-RAM. This memory stores information in the form of magnetic orientation and is built from a grid of cells, as shown in this picture. Now, one cell of this memory consists of 2 components, one NMOS transistor and one magnetic tunnel junction. Now, this last part consists of 2 ferromagnetic layers, one free and one fixed, separated by a thin insulating layer made of the following chemical elements. For the free ferromagnetic layer, the direction of magnetization can be modified, whereas the direction of magnetization for the fixed is unvariable. Now, inside the magnetic tunnel junction, an effect called tunneling magnetoresistance, or TMR, can occur. This effect is a change in the value of the electrical resistance of a material when an external magnetic field is applied to the free ferromagnetic layer, which in turn changes its direction of magnetization. Now, there are 2 possible states. if the modified direction of magnetization is parallel to the direction of magnetization of the fixed ferromagnetic layer, then the value of the electrical resistance of the material is going to change to a low value. If the directions are anti-parallel, then the value of the electrical resistance changes to a high value. Now we can change from one state to the other if we induce sufficient current through the magnetic tunnel junction in that direction. And we can go from the other state if we induce currents in that direction. This effect can be mathematically expressed with the following equation where R sub H and R sub L stands for high resistance and low resistance respectively. Now, this is the third part of the background, logic implementation in lookup table, or LUT. Lookup table is a small memory, and when programming its content, we can implement an arbitrary logic function. And the one that we're using is that of XNOR gate. And you can see in this picture an example of a lookup table using this XNOR gate. Now, as I mentioned, lookup tables are programmable, and this ability allows semiconductor industries to hide the identity of chips and safely outsource the fabrication. Here are two pictures of the design of the two XNOR gates. One is conventional and the other one is non-conventional. This is the one that we're using. And the difference between these two is that for the non-conventional design, the intellectual property is hidden from hackers when it is outsourced to foundries. Now, this memory can be combined with the STT-LUT technology. And the magnetic tunnel junctions are going to be the cells of storage of the memory lookup table. We can program the magnetic tunnel junctions so that we can hide the identity of the integrated circuits. Now, the purpose of this research are finding a relationship between power and delay of the STT-LUT with respect to TMR values, then optimizing the TMR to improve the power and delay of the STT-LUT circuit, make recommendations for decide TMR from the MTJ device, and compare it with the non-secured standard design. Now Taimoor is going to talk about the results and the conclusion.
Thank you, Michael. As Michael mentioned about the background, and I hope you have a little more understanding of what we're about to do. This is what we actually did during the whole research of 10 weeks. How the process went is the first thing is we did the circuit simulation of STT-LUT using the Hspice tool. It's a program that we use to, the example is right here. And our main concern was the delay, power delay product, and which is a product of delay and product. And here we measure the delay by using the Hspice tool. As you can see, is measuring from the clock input to the edge of the clock output. That's how we measure the delay. What we had within STT-LUT. And similarly, we also measured maximum delay from the clock to output to the clock to inverted output, as shown in the figure right here. All the results we got were based on basically power delay and power delay product. The first one is power. As you can see the trend, we, as Michael mentioned earlier, this equation for TMR, we have two variables that are shown here, high resistance and low resistance. But we have another resistance that's called reference resistor, which was kept constant throughout the whole simulation process. We also kept the low resistance constant as you can see on the right side of the graph. And this graph was plotted between power and the TMR. And looking at the trend, as the TMR was increasing, the power was decreasing. And between where we started actually from was right here when we started this 10-week internship, and then by the end of the week we were able to get to this kind of result because that was our main goal, to have a least power dissipated throughout the whole process. And as far as for the delay, it had kind of similar trend, but if you see, the trend is pretty much the same, but it comes to a saturation point. And the saturation point is causing because of the voltage cap we have. Since the supply voltage is the constant throughout the whole process, because of which it cannot exceed the supply voltage and cause the saturation. Similarly, as the TMR is increasing, you can see the delay is decreasing, and it also yields a high resistance difference. So our main concern, as I mentioned earlier, that power delay product, this is what we actually care about, because that's what the lower power delay product will be able to achieve, the better our STT-LUT will work. So as the TMR is increasing, same trend as we had for the delay. There's a saturation point again. We got, and if you see from the best case scenario to the worst case scenario, or best case scenario to the, sorry, opposite. But worst case scenario to the best case scenario, we were able to get a difference of 4.26 times. And we were able to achieve a better power delay product. So as I mentioned about the reference resistor, so after choosing a value of 400 TMR, then we had to optimize our reference resistor to get a much precise and better results. And the TMR that we were able to get, 400, was keeping the RL constant at 20 kilo ohms and changing the RH to 100 kilo ohms, and that's where we got the TMR value. And if you look at the power delay product versus the reference resistor, by optimizing, we were able to decrease the power delay product to 0.04077 value, which was the lowest throughout the whole 10-week process we were able to achieve. Here is the comparison of STT-LUT with the standard design, and it's based on the activity, and activity is basically the rate of the output switching. And as you can see here, this is STT-LUT, which is independent of the activity. Activity is not affecting it at all. Whereas if you take, in this case, we took the NAN for output 2, and when we compared it, it was depending on the activity because it depends on the gates. And if you see, in the start, we had a difference of 3.17 times, whereas at the end, as the activity increased, we had a difference of 1.41. When comparing the delay of STT-LUT with the standard design, we saw that there was a higher delay in the STT-LUT by like 10 times, which probably sounds a lot, but it's basically a trade-off for the hardware security. We were trying to save the intellectual property of the device, and the delay overhead can be overcome or can be avoided by implementation of STT-LUT only at the non-speed critical components, which are the components that doesn't really need the speed, that doesn't depend on the speed. After doing our research or getting all the results together and comparing it with the standard design, then we did a feasibility study to see like what has been manufactured in the industry. And after reading a bunch of articles and like going through a lot of research, we were able to find the highest TMR that was reported was 600. So ours was 400, which fall below that. And I wish we had like a little more time to like make the results even better. But there's no obvious trend in the whole like graph, just because there was different design targets depending on what the paper is talking about. So, but again, this was basically a trade-off for us for the hardware security with the delay. And in the conclusion, what we learned from this research was the higher the value of TMR, it yields to a lower power and delay. And reference resistor is another way of optimizing and getting like precision results. Also, these optimizations can also enhance the hardware security. And throughout this whole program, I think being a first generation college student, I really availed this opportunity to like get more hands-on experience and to learn. And especially since I was at Kenyatta College and I got accepted to San Francisco State, and going through the summer, I got connected to the faculty and I pretty much knew everyone once I like transferred to my department. And it was really good. And I like say it, I was thankful to Dr. E that he was able to get us this opportunity.
The thing is that when I was prepared before taking this summer internship, and I was lucky to be involved in the electrical engineering group, so I didn't have a lot of difficulty to understanding the concepts behind it. And another good part about this research was that we learned how to do a presentation, how to make a report of everything we have done so far, how to make also, how to work in teams, how to learn time management, how to find the most efficient ways to get the work done, and also how to, I mentioned work in teams, right? Yeah, okay.
Most importantly, we're publishers now, so we got our name on the poster too. So it's a plus.
Yes, and there is something else too. I wanted to try how doing research is in areas of engineering because I have never tried doing that. So after doing research last year, I was able to realize that I like doing that kind of tasks, and that also encouraged me to do later research when I'm doing, by the time I'm doing my my major, which is industrial engineering, and maybe do something great. And that's one of my goals, to do something that makes that makes a progress in humanity. So I really hope to do that someday. Do you have something to add? No. So thank you so much. Do you have any questions?
It's 10 weeks. Yes. And it was at SST campus in the lab. So we were like basically 4 groups: computer, computer, civil, mechanical, and electrical. So every group had like about 4 students, and we were assigned a mentor, most likely like a grad school student from SF State, and a professor whose project we were working on. Yes.
How did you feel about being assigned to a project that's not necessarily the mechanical,
Yeah.
electrical project, the civil?
Has nothing. I think that it's always good to try things that you don't know. And as I mentioned, I was lucky to have studied something related to electrical engineering. If I haven't studied that, I wouldn't I wouldn't have said not to participate to electrical engineering. I would have liked to participate. And I think I'm also aware that I have searched in the internet internships about my major, and there are none of them. So that also encouraged me to participate or get a little bit of information about other types of engineering.
I think for me, I think doing electrical internship, even like, I think I was able to. I never wrote a technical paper before. That was one of the pluses, and plus also like I think it's helping me now since I'm taking upper division courses, linear system analysis that I have to take, and I think it's circuits. It's pretty base of it, so that was really